Hello, welcome back. We have been talking about electricity and magnetism, and we saw that a moving electric charge can create a magnetic field, and that a changing magnetic flux can also induce an electric current. So we saw that electricity and magnetism can interact, and now we're going to look at how those interact in the sense of moving as an actual wave. We're going to look at electromagnetic fields and waves. To get started, the first thing we need to do is review an idea that you would have seen in previous classes about relative motion. So here's a very simple diagram. We have Alec right here, standing still, and Brittany is running really, really fast. She is moving with a velocity v relative to Alec. And she is carrying this positive charge Q. So the positive charge Q is moving with velocity v relative to Alec. So Alec sees a moving charge, and as we just said, a moving charge will create a magnetic field. However, from Brittany's perspective, the charge is at rest. It's just in her hands and they're going at a constant speed. So it's just at rest as far as she's concerned. So the magnetic field for her is zero. So if that's true, how can we have one person see a magnetic field and the other person not see a magnetic field? Is there a magnetic field or is there not a magnetic field? Now let's look at a different situation. So let's say that there definitely is a magnetic field, that Alec has created a magnetic field. He's turned on his super magnet and he's got a uniform magnetic field. Now charge Q is moving through a magnetic field. So now if charge Q moves through a magnetic field that's established by Alec, then Alec's going to see that it's moving with velocity v, and we curl our fingers into the screen. Our thumb will point up, and so there will be a force on this moving particle, on this moving charge particle inside the magnetic field in the upward direction. So Alec predicts an upward magnetic force on the moving charge, which will accelerate it, because we remember, of course, that F equals mass times acceleration. So if there's a force, then it will accelerate our particle. From Brittany's perspective, however, the charge is at rest, so there can be no magnetic force on the charge. So does the charge accelerate or not? Well, let's break this down. So if we're looking at different reference frames, Alec, reference frame A, right here, is sitting still, and Brittany, in reference frame B, is moving, and moving with a velocity with respect to reference frame A of VBA. So that's with respect to reference frame A. Now the figure shows a charged particle C. So in this case, we have a charged particle C right here, which can be measured by experimenters in the two different reference frames we're thinking about again. Reference frame A just is still, as far as we're concerned, and B, which has a velocity of VBA with respect to A. Now, the particle's velocity relative to frame A is going to be different from the velocity in frame B. It will be VCA, and that will be equal to VC with respect to B plus the reference frame A itself, VBA. So those two things are different. But what we can do is we can look at this equation and we can take the time derivative of it. So if I take the time derivative, I say dVCA dt is going to be equal to dVCB dt plus dVBA dt. Now, we look at the graph here and we see that VBA is constant. It's constant. That means it's not accelerating. There's no change in that velocity. VBA is a constant, so the derivative of a constant is zero. So this term is zero. So what we see is the derivative of VCA dt. We know that that's the acceleration. That's the acceleration, ACA. and that's going to be equal to dvcb dt, the acceleration cb. So the particle's acceleration is the same in both frames. We see that ACA equals ACB, so it's the same acceleration. And we remember F equals ma. So since F equals ma, we know that that if the accelerations are the same in both frames, the forces must also be the same, because F equals ma. And therefore, Fa, the force that the particle experiences in A, will be equal to Fb. So let's look at how we can reconcile what's going on. So in A, the force on Q is due to a magnetic field. We saw that. And that magnetic field is P sub A into the screen here. And its velocity, as far in reference to reference frame A, is VCA. So we remember that the magnetic force is going to be equal to QV cross B, where V in this case is our VCA here. So we can rewrite this as FA equals Q VCA cross B sub A. So according to Alec in frame A, a charged particle moves through a magnetic field and experiences a magnetic force of Q VCA cross B sub A. Now, let's suppose that we have Brittany in frame B running alongside the charge with the exact same velocity. So this velocity that we have right here, which is the velocity of the charge, VC, with respect to A, will be equal to Brittany's velocity, which is the velocity of Brittany with respect to A. So in that case, we could then, if we look again here at our force that Alex sees of Q VCA cross B, we can take the fact that VCA equals VBA, so I can plug this in here. And so I can rewrite this as the force is equal to Q VBA cross B sub A. So since that's true, let's now look and see how we can relate these two reference frames. So in A, we see the force on Q is due to the magnetic field, like we just saw, FA equals Q VCA cross B sub A. However, in B, Brittany sees a stationary charge. So the charge isn't moving, but there is an upward force. So it's a stationary charge with an upward force. We know that a stationary charge is not going to have a magnetic force, so it must be an electric force. So she must be observing an electric field. So for Brittany, the force is upward on a stationary charge. So it must be an upward electric field. So as far as Brittany is concerned, there is a force that is acting on the charge due to the electric field E sub B. Now we know that the force that is observed in reference frame A is the same as the force that's observed in reference frame B. The accelerations are the same. We remember that the force observed in reference frame A is due to the magnetic field, so that's QV cross B. And the force in B here we see is equal to the electric field, so that's Q times E, or Q E sub B in this case. So we can set these two equal to each other since FA equals FB. So now Q E sub B equals Q VBA cross BA. And so if I divide through by Q, so I'm going to divide through by Q, I can then see that that the electric field in B is equal to VBA cross B sub A. So that's how we can transform the electric field that we see in B. So what we notice is that whether a field is seen as electric or magnetic depends on the motion of the reference frame relative to the sources of the field. Let's generalize this finding a little bit. So this was very specific. Now let's look and see what happens if we have some sort of electric and magnetic field in frame A. So let's say that we have a magnetic field that is into the screen. So our magnetic field here is into the screen. Now we have an electric field that is going at a 45-degree angle to the horizontal here. And our charged particle is moving with a velocity VCA. So in this case, the force on our charged particle will be equal to the force due to the electric field. So that, of course, will be the force due to the electric field will just be Q E sub A. And the force due to the magnetic field will be equal to Q VCA cross B. So combining these, we can just add those together, and the total force is going to be Q E sub A plus V sub A, VCA cross B sub A. And so a charge in reference frame A experiences both electric and magnetic forces, and that we can combine those right here. Now, in reference frame B, the electric field is just an electric field. And in this case, the charged particle, because the charged particle is at rest, so there is no magnetic field, just electric field. And so in this case, we see that the electric field must be equal to whatever electric field is in A plus VBA cross B sub A. So if we generalize it, we see that our QEB must be equal to what we had in reference frame A, which was Q times E sub A plus VCA cross B sub A. And so since these were equal, we could cancel, we could divide through by Q, and we see that we can generalize this and say that the electric field in B can be transformed as E sub A plus VB sub A, where we say that V sub CA is equal to V sub BA. Those are equal to each other because that's how the reference frame is moving, crossed with B sub A. So we see that the charge experiences the same force in frame B, but it is due only to an electric field. So that's how we can transform our electric field. We see that the electric field is going to be transformed by taking basically a piece of that magnetic field. Now let's go back to the question about how we transform our magnetic field. So we had this question where we saw in this case, Alex sees a moving charge and he knows that this creates a magnetic field. So Alex sees it moving, but Brittany's moving, but Alex at rest. So now from Brittany's perspective, the charge is at rest, so the magnetic field is 0. So now we've got to figure out, is there or is there not a magnetic field? So how do we resolve this? Well, let's generalize this problem as well. So here we see a charge at rest in frame A. So here we have, this is what we just saw. So this time our charge is at rest in frame A and is moving at rest in frame A is moving in frame B and creates a magnetic field, B sub B. So in frame A, the static charge creates an electric field, but no magnetic field. So in this case, the electric field is equal to 1, we know comes from a point charge. So the electric field is what we see in A. It's equal to 1 over 4 pi epsilon naught, Q over R squared, R hat. Now in B, the moving charge creates both an electric and a magnetic field because it's moving as far as B is concerned, because B is moving away from it, but it was actually sitting here still in frame A. And so we see that the speed that the charge will experience, that B will recognize that the charge has, because it's sitting there in frame A, but B is moving away from it. So Brittany is running away. So that will be negative V sub BA. And so the electric field that this charge will have will be the same in either frame because it is just a point charge and it doesn't matter if it's moving or not. And so the electric field will equal the electric field in A, which is equal to 1 over 4 pi epsilon naught, Q over R squared, R hat. And that is just the electric field due to a point charge from Coulomb's law. Now, the magnetic field that that is seen from reference frame B is going to be equal to what we get from the Biot-Savart law. So the magnetic field is going to be equal to, now it's moving in the opposite directions. That's where the negative came from, because because B is moving away from the charge. So we have negative mu naught over 4 pi Q over R squared V sub BA cross R hat. Now, if we take Q over 4 pi R squared right here, I notice that this looks very similar to my electric field. So what I could do to get that to be more similar is I can multiply this just by 1, which is the same thing as multiplying it by epsilon naught over epsilon naught. And now I'll have an epsilon naught in the denominator and 1 in the numerator. And so this would then be epsilon naught mu naught times VBA, and I can pull out this term 1 over 4 pi epsilon naught Q over R squared R hat. And I see that this term is the exact same thing as the electric field right here. So this term is the electric field. And so I can say that the magnetic field is equal to this term right here, negative epsilon naught mu naught VBA crossed with the electric field in A. Now, if there had already been a magnetic field in B, we could in A, then we could say that the magnetic field in B would also be equal to the magnetic field in A added to this term. So adding on the same term that we had here before. Now, let's look more closely at what this is. These are these two constants that we keep using. You kept asking me, why do I have to use 1 over 4 pi epsilon naught? Shouldn't I just use K? Well, epsilon naught is an important constant, and we're going to see why. So epsilon naught times mu naught. If we do 1 over the square root of those two terms times each other, so 1 over the square root of epsilon naught times mu naught, if I multiply them together here, I see and that I get 8.85 times 10 to the minus 12 times 1.26 times 10 to the minus 6 raised to the negative 0.5 raised to the negative 1/2, and that gives me 2.99863 times 10 to the 8th, and and that is in meters per second. So this should be a very familiar term. This is the speed of light, c, the speed of light. So putting this in for our term here, we see that we can say, well, in that case, if I want to solve for epsilon naught mu naught here, so epsilon naught mu naught is going to be equal to 1 over c squared. So I can put this in right here. And I see that my transformation for the magnetic field is equal to B sub A minus 1 over C squared V sub BA cross E sub A. So our two transformation equations that we have are called our Galilean field transformation equations. So if we have a moving charge moving in a certain reference frame, we know that the electric field transformation will be equal to E sub A plus V sub BA cross B sub A. And that the magnetic field will be equal to B sub A minus 1 over C squared VB sub A cross E sub A, where VB sub A, or V sub BA, is the velocity of reference frame B relative to frame A. And the fields are measured at the same point in space by experimenters at rest in each reference frame. And now these equations are only valid if V sub BA is much, much less than C. If it's not, then we get into relativity. So what we see is that the electric field and the magnetic field are intimately related to each other. And whether something is being affected by an electric field or a magnetic field depends on the reference frame. And we've seen how we can actually transform our electric field and our magnetic field if they are in a moving reference frame based on the Galilean field transformation equations.